noise in differential pairs. With our understanding of noise in basic amplifiers, we can now study the noise behavior of differential pairs. Shown in figure A differential pair can be viewed as a two-port circuit. It is therefore possible to model the overall noise as depicted in figure B for low frequency operation. The magnitude of IN in square bar is typically negligible. To calculate the thermal component of Vn square in bar, we first obtain the total output noise with the inputs shorted together. Figure A, nothing that superposition of power quantities is possible because the noise sources in the circuit are uncorrelated. Since IN1 and IN2 are uncorrelated, node P cannot be considered a virtual ground, making it difficult to use half circuit concept. Thus, we simply derive the effect of each source individually. Depicted in figure B, the contribution of IN1 is obtained by first reducing the circuit to that in figure C with the aid of this figure and neglecting the channel length modulation. The reader can provide the half of IN1 flows through RD1 and the other half through M2 and RD2. Here you can see in this figure A differential pair, B circuit including input referred noise sources. As shown in figure D, this can also be proved by decomposing IN1 into two correlated current sources and calculating their effect at the output. Thus, Vin out M1 is equals to IN1 by 2 RD1 plus IN1 by 2 RD2. Note that two noise voltages are directly added because they both arise from IN1 and therefore correlated. It follows that if RD1 is equal to RD2 is equals to RD, Vn out square bar M1 is equal to IN1 square bar RD square. Similarly, Vn out square bar M2 is equal to IN2 square bar RD square, yielding Vn out square bar M1 M2 is equal to IN1 square bar plus IN2 square bar into RD square. Taking into account the noise of RD1 and RD2, we have the total output noise Vn out square bar is equal to IN1 square bar plus IN2 square bar RD square plus 4k TRD is equals to 8k T 2 by 3 GM RD square plus RD. Dividing the result by the square of differential gain GM square RD square, we have V in IN square bar is equal to 8k T 2 by 3 GM plus 1 by GM2 RD. This is simply twice the input noise voltage squared of a common source stage. Here you can see in this figure calculation of input referred noise of a differential pair. The input referred noise voltage can also be calculated by exploiting the lemma illustrated in figure. As shown in figure, the noise of M1 and M2 is modeled as a noise source in series with their gates, and the noise of RD1 and RD2 is divided by GM2 RD2, thereby resulting in equation. It is instructed to compare the noise performance of a differential pair and a common source stage as expressed by equation. We conclude that if each transistor has a transconductance Gm, then the input referred noise voltage of a differential pair is root 2 times that of a common source stage. This simply because the former includes the twice as many devices in the signal path, as exemplified by the two series voltage sources in figure. Since the noise sources are uncorrelated, their powers add. It is also important to recognize that with the assumption of the equal device transconductances, a differential pair consumes twice as much power as common source stage. With the transistors have the same dimensions. The noise modeling of figure can be rarely account for 1/f noise of the transistors as well. Placing the voltage sources given by K by C naught X WL in series with each gate, we can here you can see in this figure alternative method of calculating the input referred noise. Rewrite equation as Vn square in dot bar is equal to 8 kT into 2 by 3 Gm plus 1 by Gm square Rd plus 2K by C naught X WL into 1 by F. Does the tail current source in figure contribute noise? If the differential input signal is 0, the circuit is symmetric. The noise is ISS divides equally between M1 and M2, producing only a common mode noise voltage at the output. On the other hand, for a small differential input delta V in, we have delta ID1 minus delta ID2 is equal to Gm delta V in is equals root over 2 nu n C naught X W by L ISS by I in by 2 delta V in, where I in denotes the noise in ISS and I in less than ISS. In essence, the noise modulates the transconductance of each device. Equation can be written as ID1 minus ID2 similar to root 2 nu and C naught X W by L into ISS by 2 into 1 plus I in by 2 ISS into delta V in is equals to Gm naught 1 plus I in by 2 ISS delta V in, where Gm naught is the transconductance of the noiseless circuits. Equation suggests that as the circuit departs from equilibrium, In is more unevenly divided between M1 and M2, thereby generating differential noise at the output. This effect is nonetheless usually negligible. The effect of noise must be studied for many other analog circuits as well. For example, feedback systems, op-amps, and band gap references exhibit interesting and important noise characteristics. We return to these topics in other chapters. Thank you.